All right, so this is our last topic, which to you guys, you're like, yay, hooray. So am I. But it's a little bizarre for me because usually we would have then like a couple days of review of all the stuff from before. And a question, and we can refine it at the end, is if we want an office hour tomorrow or not. That may be more for major, and we can talk about it. And so the QA lab, so QA3, I made it due Saturday, more for the people who are in the evening group, because a lot of them work during the day. So if you're a procrastinator and you wait until things are due, the QA3, and then there is a QA2 that's going to be due next week in the middle of the week. They are both like 9 or 10 steps. So just be aware of that. The QA1 was just so we got the idea of how things flow. You're going to have to read. Some of you still are a little resistant to that, but you're going to have to read the intro and the procedure. I gave you also the procedure because some people actually can help them. But yeah, I do expect with each flow chart. So I look at the first one that we've got the idea down, and most of you had a theme and went with something. And some of you, it's wonderful, and just keep going with that. And some of you, I wrote a note that said, great, now let's like up our game here a little bit. Yeah. The other big thing is your demo. So since it's Thursday, when I see most of you again, it will be Monday, and our demos are on Tuesday. So if you have not talked to me, you need to be talking to me today. You're supposed to have an idea in today. So during a break, you can talk to me, or staying after, or emailing me. So the only thing that's going to be happening on Tuesday is the demos, and it will be presentations like before. Depending on your demo, a lot of you will be taking what they did last year. It was about 50-50 split. Most people did a PowerPoint, and they either embedded a video of them doing the demo, or they embedded pictures. And so that way they were able to have background. There's 1 or 2 people who did it with just the video, and in the video they're explaining stuff. So I am expecting that you're going to give some of the chemistry and science background behind your demo, and what's going on, and what worked, what didn't work, and stuff. And then you're also writing it up. And so there's instructions on there. So if you have questions on that, Monday would be a perfect time to ask about that. All right. So oxidation reduction has to do with the movement of electrons. And why we get to revisit that is because we are going to use this equation later today. And you can see there's a Q in there, and we will get to the equation that has the delta G, and there's also a way to get to K and stuff. So it really pulls everything together. And so a lot of the questions some of you are asking me about the worksheet that's due today will kind of get answered as we're going through this. But initially, I have to reteach you how to do a balanced equation with oxidation reduction, because we always looked at really simple ones. And we're going to do that one first. So I usually talk about this one because it's usually you all did this in lab in 221, which is you took a piece of zinc and you put it into a solution of copper sulfate, and the zinc disappears into the solution, and you end up with copper metal. The sulfate is actually a spectator here, so we can ignore that. So the copper is a +2 charge. So zinc is a solid. And so normally what we would do to write the equation is we'd say zinc plus copper ion goes to zinc ion plus copper solid. So that's like how we would always write it. We would, back in 221, we would have included the SO4, but we're going to be leaving, you can see everything has charges because they're leaving the spectators out. What we're going to do is half reactions. And we've seen the idea of half reactions, but these are true half reactions for oxidation reduction. one of the reactions is going to be the oxidation and one's going to be the reduction. And so you start with, doesn't really matter, we'll say the zinc, and the zinc is going to go to zinc ion. So that's its half reaction. And then the other half reaction would be copper ion going to the copper solid. Now the ions are aqueous, so I just, for purpose of teaching, I just leave off the aqueous. You have to show the charge. That's the whole key of oxidation reduction, is this change in charge. Now, there is something terribly wrong with these half reactions. Does anybody know? The board's clean. It's another chance for bonus points on the board.
Arrows?
No, my arrows are okay. They're not actually balanced. So it's like, what do you mean they're balanced? There's one zinc on each side, there's one copper. And it's something I referred to at least once before. You also can look at charges. When we were doing conjugate acid, conjugate base, acid base reactions, I commented you can also look at the overall charge, and the charge has to be the same on the two sides. And so you cannot change the charge of the zinc or the copper ions, but the piece that's missing from our half reactions is an oxidation reduction. There's always electrons in the half reactions. They're not going to be in the overall. And so for this to be balanced, we would have to have 2 electrons on the product side for the zinc, which indicates that it's losing electrons. And then for the copper, the 2 electrons would be on the reactant side, which indicates that it's gaining electrons. So it's just another way of seeing oxidation reduction. So which one's the oxidation and which one's the reduction?
Zinc one would be oxidation, and then the copper one is reduction.
Yeah, so we have like 10 different teachers taught you guys oxidation reduction here. I teach it, it's why I'm dressed like a lion today, is the acronym LEO-GR. So Leo's a lion. Oh yeah, we're still in Leo season, so it's perfect. And so here's Leo. He's our little lion. He's got his RedOx bow tie on. And so Leo, lions growl. And so what this stands for is losing electrons, and the O is for oxidized. So my zinc is oxidized. And the GR stands for we're gaining electrons. Can't write it. I was hoping for blue, but my blue's not working. Gaining electrons is reduced. So the copper is reduced. So the half of reactions allow us to see the LEO-GR. All right, so we're going to do it. Let's do it with this one that I kind of covered up there. So go ahead and write your 2 half reactions. When you write your half reactions, make sure before you start adding electrons that the elements are balanced. Adding the electrons is the last step. So make sure, because like the iodine, I can see we're going to have to balance that. Yeah, I'm gonna write Perry's name up. Look at that, Perry, you're gonna be the first one. All right. So you pull the chromium and you don't switch sides. Somebody said the arrows, we're going however I give it to you. So the chromium +2 stays as the reactant, the chromium +3 is the product. So I have 1 chromium on each side. Now I have to balance. The difference between a +2 and a +3 is 1 electron. This, for some reason, is the difficult question for some of you. Which side does that 1 electron go on here?
The right side.
Yeah, and so I never use lefts and rights because they're reversed for many people, but it goes on the product side, would be what we would say in chemistry. I would, if you learn nothing else from me, most people have their lefts and rights backwards. And so it's also a sensitivity for other people too. So they differ by 1. The electron has to go on the side that is more positive. So the net on this side will now be +2. All right, our other half reaction is the I2 to the I-. So however I originally give you that, they stay on the same whatever side. We have to balance the iodine first. Balance the iodine or whatever your other elements first. So now I need, oh, and you want to show your state of matter. Oh, I didn't show it, but the iodine is probably a solid in my original equation. Yeah, good job. The electrons, when you write the half reactions, will always be on opposite sides. So if in the one they're on the product side, my other one, it should be on the reactant side. And I do need 2 electrons here because I end up with a -2 here. So that comes out balanced. Now, before we put it together, because this one we're going to put together, there's another step. The questions up to that point. And you can also then write your Leo Gur. So this one's losing, so this is my Leo. You can actually just do one of them. And so as soon as you know whichever one is losing, the electron is a product, it's losing. And this one is my gaining. My Gur is my iodine. When you add the 2 reactions together, that's what my step 3 is here. There is a multiplication factor is what they call it. And it is that the electrons have to cancel out. You have to have the same number of electrons in each half reaction. So the multiplication factor is we're going to have to double the chromiums so that we have 2 electrons in each. So the electrons must cancel out. The electrons gained must be the same as the electrons lost. These are really simple ones that we're starting with, so you see the hang of it. Where we're going with this is we're going to make them acidic or basic. So today we're going to make them acidic. All right, and so once you add them together, the electrons are gone. And so our balanced equation is 2 chromium ions. It does not matter the order you write them in. It does matter which side of the arrow you write them on. And then we end up with 2 chromium plus 3s plus the 2 I negatives. So it's really easy on this one to see the chromiums. We have 2 chromiums, 2 iodines. You want to always make a quick check that your charges are the same on both sides. So I have a 2 times +2. So I have a +4 on my reactant side. And on my product side, I have 2 times +3. So I have +6 and then -2. So they're equal. They're both +4. All right. So I'll give you a moment to try this one, and then we'll look at how to do acidic ones. So do your half reactions, figure out which sides your electrons are on, identify your Leo Gur, because we start adding to the Leo Gur part too, and then bring them together. This is red, so watch over you. It's the 3-legged ox, because I dropped her. It's traumatic, but she's okay. And every once in a while I put on the jacket that has the missing leg. And she sparkles. Can you guys see the sparkles? It's kind of nice. Maybe only I can see the sparkles. Is anybody in here a Leo? I know Tristan is because he had, oh, and Major must be a Leo. That makes sense. Anybody else have a birthday this term? It's kind of funny. This is like the term of all the Leos. All right. So the good news is the worksheet for this is due Monday. So you have that nice long weekend. Oh, it's only 3 days, right? To forget or remember. It is actually up there in the week 5 folder. So I would totally do the folders different. I'm a fan of how Blackboard and me get along right now. So splitting our 2 half reactions, and there's 1 tin we have to do. So with the tin equation, difference is two electrons. which side gets the 2 electrons for the tin?
The product.
Yeah.
I mean
so
the reactant. Yeah, the product.
product. So right, so +4 and -2, because electrons are negative, will get us back to +2, and that makes sense. The iron would be there. It is purely coincidental that I keep writing the Leo first when I'm writing them. That's totally random. Sometimes Leo will be first, sometimes not. But the Leo is the one losing, or the reduced element. So we would say tin becomes reduced to the +4 state. All right, we have to then double our second equation so that we have 2 electrons. 2 is a really common number, but it's not the only number we're going to see. These were all simple metals. And that's not how most reactions happen, because oxygen is so freaking greedy that almost every reaction is going to involve an oxygen somehow. All right, so our electrons cancel, and we have tin +2, 2 irons with a +3 going to tin +4, and the 2 irons with a +2. So our original equation, what was wrong was we had a +5 charge to start and a +6 charge to end. So that original equation was not balanced. All right, questions? So now we're going to add the next step. And we'll do this first one. So the first step is you write your 2 half reactions. So we want the MNs in 1 half reaction. Anybody know what MnO4's name is?
Manganate?
Permanganate, actually. There is no such thing as manganate. Fascinating. So there is a reason it is called permanganate. And it has to do with the oxidation number of the manganese in it. That's actually where a lot of the systemology came from. And then does anybody know what the C2O4 is? -2?
Is that oxalate?
I was going to say it starts with the ox, coincidentally. It is oxalate. So that's kidney stones are either oxalates or not. All right, so the half reactions, we've got that. So we'll look at the manganese one first. We have an extra step, which is oxygen. But these are acidic, which means they're aqueous, which means there's lots of water around. So we're not going to have oxygen as O2 in any of these reactions. First step is you always balance the elements other than the oxygens and the hydrogens. The next step is, so we have 1 Mn on each side. You balance the oxygens by adding water. So I have 4 oxygens here. I add 4 H2Os on my product side. And then I balance the hydrogens because it's acidic. We're going to do it with hydrogen ion, even though hydrogen ion isn't actually there. Why? It's not our correct way. We'd say 8 hydrogens. It's proton. And it actually isn't ever hydrogen by itself. It's always hydronium because the water is what pulls it off and holds onto it. And then we balance the charge with the electrons. So how many electrons and on what side for the Mn?
+2.
Anybody see? 5. So we have a +8 and a -1. So on this side right now, I have a +7 total. So you're looking at the whole side. On this side, all I have is a +2. So the difference between the 2 sides is 5, right? So I need 5 electrons. The next question is, which side gets the 5 electrons? Electrons are negative.
The
So you want to
reactants.
put them on the side that has the higher number right now. So the reactants get 5 electrons. All right. The electrons, It's something new. And I would recommend redoing. We're going to do these two problems of redoing them sometime over the weekend so that you have it down. All right. So on the second half reaction. Oh, by the way, that first half reaction, is that Leo or Gur?
Gur.
It's gaining, right? So the electrons are going into it. So we'll just write Gur for right now. All right, on the second half reaction, you want to be careful. Students get really excited about doing the water hydrogen thing. The first step is the other elements. So you have to remember to balance the carbon. So always start with your other elements. Oh, look at that. We don't have to deal with water. So I have 4 oxygens on each side. If I don't have to add water, I don't have to do anything with the hydrogens. But you always have to do something with the electrons. So this one's easy. There's no charge on this side. The CO2 should have been a gas. And this is why I've been really particular about some of you are a little lax in showing your charges. That's like going to break your game in this because oxidation reduction is all about the charges. So we have a -2, so I need 2 electrons on the product side. That one makes sense, gives me a -2 on each side. And this one's losing the electrons. So oxidize, so that's Leo. And now we have to add it together. To add it together, one thing has to cancel out. What has to cancel out?
The electrons.
The electrons have to cancel. So that Mn equation, you got to multiply everything by 2. And the carbon equation, you got to multiply everything by 5. This is where using different colors is helpful. I don't recommend you erase. I recommend, and usually writing, like I'm going to multiply this all by 2, that writing the numbers above, like crossing them out and writing your new numbers above. So I'm doubling everything in this one. And, all right. And in my second equation, I'm going to multiply by 5. And it's again, you got to cancel those electrons out. So 5, and that will be 10. So you can cross your electrons out. Some people like to, some people don't see a need to. And then we went and bring it all down. Now, something I said, the order doesn't matter as long as you have the correct things on the reactant side, the correct thing on the product side. There is a convention that will make it easier for you and especially for me, that if there are hydrogens or water, they are always shown either first if it's on the reactant side, or they're shown at the very end if they're on the product side. So if you have hydrogens or water, you either show them at the beginning on the reactant side or at the end, and then you put the other stuff. And then we want to check if it's balanced. And there is a quick way to check that I will show you in a moment. You can go through the whole balance thing. Do I have the right number of carbons? Do I have the right number of oxygens? A quick thing, if the oxygens are the same and the charge is the same, you're going to be good to go. So I usually just check my oxygens. And so I have 8 plus 20. So I have 28. And here I have 20 plus 8. So we're good. There's 28 oxygens. So that's why I said check. I just check my oxygens. You can check all of them. And then I look at the charge, which can be a little gnarly for some students. But this is a plus 16, minus 2, and then that's going to be minus 10. So the coefficient does affect the charge. So that is giving us a plus 4 on this side. On my product side, oh, this one's easy. All I have is the 2 times the plus 2, and so I have a plus 4. So we're good. Questions? All right.
Alright,
So
where's the minus come from? On the reaction
Mm.
side.
I can't hear you. Minus what?
The minus sign.
There's a 5 coefficient.
Oh,
And
understood.
you,
Okay, got it.
this is why I keep saying you guys have to respect those charges. -2 or 2 minus. So the 5 times -2 is -10. Is that what you were asking? Sorry, your audio sometimes cuts in and out. His question's really important because when we do this in person, I can go around and that's what everybody else is always asking. So I'm going to pause us. If you're watching along at home, you want to pause and try this one. All right, let's go for it. If you're on track, just keep going. So split it into your 2 half reactions. That step everybody gets. So 2 half reactions, and then you have to balance the other elements before you start adding the waters and the hydrogens. So we have to balance the 2 chromiums. And if you want, you can also balance your 2 chlorides at the same time. So the second equation is simple. We're just going to need 2 electrons on the product side because there's no oxygens involved. So this is my Leo. And all right, the first equation, you got to have that 2 there, else at the end it doesn't work, and then you got to start over. It's really hard to backtrack and figure out where you made a mistake because you can see all this stuff going on. And all right, oxygens, 7 waters on the product side. And that gives me 14 hydrogens. Now, the acid ones are not bad. So for Monday's study set and Monday's worksheet, they're only the acidic ones because you want to get this idea of the waters and the hydrogens, the Leo Gur, reminding yourself of it. Because on Monday in lecture, we are going to add the basic environment and it adds a twist to it. And so we're going to save that though for Monday. All right, and now we have to do the electrons. Now, one of the equations is often much simpler. So the electrons were on the product here, which must mean my electrons, they have to always be opposite. So how many electrons? Well, if we look
12.
here, my charge is 2 times 3. So on my product side, I have an overall +6. On my reactant side, I have 14 and then a +14, then a -2. So I have a +12. I think that's Damon's voice there. So the difference between 12 and 6 is going to be 6. So this is going to be 6 electrons. Yeah. All right. Now you have to have the same number of electrons. Questions to that point? So your electrons need. Go ahead.
We don't count the waters on the product side as it's like the number of like how many electrons we have.
There's no charge on water. Water's neutral, so that's why I ignored it. So the only thing that's why I only looked at the chromium. That's a really, yeah. And thank you, Major, for asking those questions because I know they're questions people always have, and they're not a question in my mind, so I never know what the questions are. All right, to add it together, you have to make your electrons cancel. So we have to multiply our second equation by 3 so that we get to the 6 electrons. And 2 times 3 is 6. And then your electrons will cancel, putting your hydrogen first or last, or waters. Now, the other thing that was nice about these, and that usually, happens with the acidic ones, only one of our reactions had the water or the hydrogen, but you could have a situation where both reactions have water. And so the waters might cancel or they might add together. All right, so 14 hydrogens. This is dichromate, and then 6 chlorides. And then 2 chromiums with a +3, and then 3 chlorine. Chlorine was a gas. And this is truly water as H2O liquid, if you like showing your states of matter. And that's sideways. Okay, I go to the dentist today and they were like, turn your head sideways, but keep it straight. And I'm like sitting there like, how do I turn it sideways? No, keep it straight. No, turn sideways, but keep it straight. And they finally, I'm like, just touch my face. And I still don't know what they were trying to get me to do. But we're going to check count our oxygens. So I have 7 and I have 7. So I'm assuming everything's going to be good. We're going to check our overall charge. So I have a +14 because the coefficient is important. I have a -2 and then I have a -6. So 14 -8. So this is a +6 overall. And then back to like the question Major has been asking. So the water has no charge, the chlorine gas has no charge. The only charge, and you do factor in that coefficient does affect the charge. So I have a +6 charge on each side, which means we did it. We're good. All right, we're gonna add one more piece to this, but any questions? It just takes practice. I recommend printing, or you don't have to print the page over, but cover up the answers and just try it again. It's actually a really nice, soothing distraction from everything else. What happened to the chromium? So what you'll see the question will say, what element was reduced? So that's where the Leo Gur is really nice. So here we're gaining electrons, right? So electrons are on the reactant side. That means we're gaining. And again, I commented, like I think we have people from 10 different, probably I'm exaggerating there, it might only be like 6 different chemistry teachers in different schools. So some people use oil rig. I don't really care what acronym you use. Oil rigs are not cuddly like Leos are, so. All right, so gaining electrons means we're reduced. So the element that's reduced is chromium. It's in the reduced state as the chromium +3, but the chromium goes through reduction. So it's always an element. This is our whole reaction for the Gur. If I ask the element that was oxidized, we'd say the chlorine. There's also that other piece, which you started seeing it on the QA labs, which is what is the reducing agent? The oxidizing and reducing agent. You guys all remember doing this, and this has to be a reactant. Kind of back to the conversation we're having in office hours, there's a cause and an effect. The oxidation reduction is really the effect. It's what happens. Something was oxidized. The agent causes that to happen. And so chemical equations are cause and effect. It's like this wonderful duality that we have on this world, right? So the reactant. So it's always the other one caused the reduction. It is the chloride. So whatever is reduced, the other one is your reducing agent. And it's the reactant of that one. You don't have to show the coefficient. That doesn't matter for this part. It does matter for balancing it. If you said 6 chlorides, that's fine, but it's not the chlorine gas. That's the effect. And then we're going to add one more piece to it, but we're going to move to a different page so I have more room. All right, again, page 52, we're going to do on Monday. We're going to do the basic ones on Monday. So just be patient. There's all these gimmicks for how to do it, and yeah, I don't know. This is also, somebody last year did this. So this picture here is the original battery. from my understanding. So there's some wonderful stories behind these. So Volta, actually volts are named after the guy who made this. And so it's a stack of, I think, I'm not going to remember if it was copper and zinc, and they were huge. It was like several feet tall, but you can do it a small stack. And then if you have a wire, you can light up something, or you can do a lemon battery, and like do different types of fruit. I've actually done that one with a bunch and see what conducts better. Anyway, so this is a battery. These are all words that mean a battery. That's why this guy's sitting here. It means, for it to be a battery, it also means that it is spontaneous. It's gonna work. The electrons flow. On Monday, we're gonna do the non-spontaneous one, which is electrolysis. I'm mentioning that right now because there's always somebody who is too smart for this. And they worked with electrolysis, and they would like to tell me I'm going to get everything backwards here. Electrolysis, you have to have it plugged into the wall. And so the electricity is pushing the reaction. It's non-spontaneous. So everything will, well, not everything, but half of the things I'm going to write down are going to be opposite. We're going to do that also on Monday. So sticking with batteries, and where we're moving with this in about 10 minutes is to delta G's. So this is, apparently I'm saying this is going to work. We're going to diagram this. So we'll write our two half reactions. So the cadmium is going to cadmium with a +2 and the 2 electrons. So that is my Leo, or whatever acronym. You can write ox if you want. You can write oxidation, and then the 2 electrons plus the nickel ion showing your charge goes to nickel solid. That's my GER reaction. So that's my reduced. So a battery, there's always a separation. So in our batteries, there's there's 2 compartments and they're separated. So we'll do the first one as 2 separate beakers, but you can also make them one. I'll do that on the next one. So in one of the reactions, you're going to have a piece of metal, and this is going to be a piece of cadmium. And you're going to be in a solution that's going to have cadmium ions. And so this reaction here is what's happening, that the cadmium solid, we're going to lose electrons, and how it's losing electrons, we have another piece of metal here, and that's going to be nickel, is you're going to have a wire. You can make your wire any way you want. My hair is curly, can't see that, but so my wire always says curly Q's. The electrons flow in the wire. And we show that the cadmium's losing. So this is my oxidation. I should have written the reactions underneath, and this is going to be my reduction. So this was, you can write the reactions underneath. We'll do it on the next one underneath. How's that? And this one, the nickel is gaining the electrons. And again, it's in the solution with nickel ions. There's also going to be anions because you can't just have cations. So they're probably nitrates. They're going to be something that doesn't precipitate with these guys. And some people will show that the cadmium, this electrode, these are called electrodes. The nickel and the cadmium are called electrodes. Those are the metals. The cadmium one's actually getting smaller because it's dissolving into that solution. And the nickel one is actually getting bigger because the nickel ions are actually plating onto the nickel. All right, this is not going to work because oh, there's two other pieces. There's a couple other pieces. One is the oxidation. The electrodes always have a name. Oxidation, this is called the anode. So the anode is always the oxidation. And the way I always get that right is they both start with a vowel. They start with an A and an O. And so I never mess it up. I never even have to look at my notes because I learned my alphabet and my vowels back in grade school. The other one is called the cathode, right in red. Reduction always happens at the cathode. Always, no matter what kind of cell we're going to be drawing. So the cathode is always reduced. The anode is always oxidized. All right, there is also for the electrodes, we have names and they're called polarity. We're going to put a plus and a minus. They don't call them a charge, they call them a polarity. The cathode is positive and the anode is negative. That's going to be different when we do electrolysis. I am 100% aware of that. We are not doing electrolysis. So whoever's watching this and wants to tell me I did it wrong, I did it correct because we're doing electrochemical. The cathode is positive. If you look on a battery, positive, there's a positive and negative on a battery. The positive is called the cathode and the negative is called the anode for every battery. All right. So there's one more piece that I'm missing. Oh, and the electrons, since reduction is always at the cathode, the electrons are always, you have to show the arrow of the electrons are always moving towards the cathode. So our battery is not going to work. There's something missing. Does anybody see what's missing? Or have an idea of what's missing? If you've ever drawn a circuit, our circuit is not going all the way around. Electrons are going that way, but we need a full circuit. So we have to make a bridge. You can make your bridge however you want, but there is going to be a bridge between the two halves. This is an ion bridge. I don't have much space. So we're going to make a really simple bridge. It's like a suspension bridge. All right, so you have to have an ion bridge. You can even, the ions are going to flow on the bridge, and it depends on what kind of ions you want to do. If you have anions, so if the ions are anions, the anions will flow opposite of the electrons. And that makes sense. This is called the anode. The anions would flow towards the anode. If you want to do cations, the cations would flow towards the cathode. But an anion is a negative charge. So our electrons, our negative charge will circle correctly. If you do cations, it's the same thing. The cations move opposite of the negative. So that is what a battery, drawing the battery is. So let's fill in down here. So the anode is what's happening at the anode again? Starts with an A.
Oxidation.
Oxidation. What does oxidation mean again?
Losing electrons.
Losing electrons. And what's the polarity if it's electrochemical, which is what this page is all about?
Negative.
Anodes are negative. All right. So it's losing electrons. Cathode is reduction. And yeah, you guys get to have, you can look at your notes and stuff because there's no way I can control that. But really, when you get somewhere else, rather than having to always look through your notes, cathode starts with a consonant. Gur is we're gaining the electrons, and cats have paws. So it is a positive electrode. The other thing about this is the flow is spontaneous. So the anode is always losing electrons. So the electrons are always flowing from the anode to the cathode because the cathode's gaining. So the flow of electrons through the wire, this would be our wire, will be that way. And then if we completed the circle, the flow of the anions will be towards the anode. If you would prefer to do cations, they would be towards the cathode. But that's just writing it in words, what you're going to diagram out. The salt bridge, I called it the ion bridge. I honestly, at this moment, don't know what the name is. I'm a biochemist again, and salt bridges exist in enzymes and all these other wonderful proteins. And so I may have taken that from my brain part, my biochemistry part there, but the salt bridge is needed to complete the circuit. The other way you can draw it, and I'm going to give you guys a moment to draw this next one then, is you can make it one big container. You can make it as two separate ones. If you make it one big container, you have to separate it. So on one side, you do your cathode, one side, you do your anode. My recommendation is either at the bottom or underneath, you write your half reaction and you add your electrons in and then label. It doesn't matter to me if the anode is on the left or the right. It does matter to me that you have everything labeled correctly. So write your half reactions, draw. I'm going to pause us. And all right, I'm resuming. So write your half reactions, and what's missing from my half reactions? Is anybody there? Maybe only Damon. He looks distracted. We're missing the electrons. So for the copper one, it is gaining. So this is going to be my GER. And the zinc one is losing. So that's going to be my Leo. I think it's really helpful to do the Leo GER. And then you can draw your electrodes. So the solid, the metal is the electrode. An electrode is a piece of metal. It's a solid. It's like these in the battery here in the lemon that you have to stick a piece of, this is a copper and a piece of zinc. You actually just use a penny and a nail is the trick, a galvanized nail. And this would be the zinc. So this is our picture here actually. All right, so this is my Leo side. You can draw your solution with your zinc and with your copper. So Leo's losing. So when you draw your wire, the electrons are going to move towards the copper because it's gaining electrons. And then you can put your bridge in. So your ion bridge will connect the two. You can make it just like, well, you can do it however you want. And so the anions are flowing opposite of the electrons to complete the circuit. If you want, you can draw a little guy fishing on the bridge. Draw a fish down here. And then a bigger fish eating the little fish. All right. You can draw a guy sailing on his boat. I don't know if everybody's back. Draw somebody swimming. Have a lot of fun. All right. You should give him a hat so he doesn't get sunburned. What am I missing from my diagram?
The connection for the salt.
Well, the salt's there. That's my anion. Missing the polarities. So the Leo is the O. So this is my anode. and the anode is negative for this one. You can write it next to it, or you can write it on the metal if you like. GR reduction is your cathode. So my copper is my cathode on this one. And so it is positive. The electrons are flowing towards the cathode. The anions are flowing that way. I didn't give myself enough space when I'm on the board. I can do, you could also do cations. So then you get to draw cats, would flow opposite of the anions. And so again, a lemon battery or a potato battery, you have to make your own, but they're really simple to make and they're really cool. Somebody did an electrochemical cell last year. They changed their demo at this point. So hydrogen fuel cells, this whole idea is of it's using water. We're using hydrogen and what you're getting out is water. So hydrogen and oxygen are going in. So you have an anode and a cathode. So it's a similar idea. It's going to be in a basic environment and stuff. And the issue with it is our economy is completely set up to deliver octane or gasoline and not hydrogen fuel. And so in this country, you would have to completely change our delivery of fuel. There's other options though that are even better that we hopefully will be getting to, but we have to get to soon. So we're gonna now put this with delta G. So with everything that we've just done. And so there's a lot of words on this page and we'll go through this. Yeah, is actually, we're gonna go back to this page for a second because I have my two half reactions here and I have space to write in. So it kind of will explain the next page, but if you have your notes, the very last page, since it's our last set of notes, there is another chart and there's tons of these charts out there. I picked one that was a smaller chart and has enough for, I'm pretty sure, everything we need. And these are what are called, these are our half reactions. All of the half reactions, as it says on the chart, are written as reductions. They're always gaining the electrons. So if these are written as reductions, what kind of agent are all of these? Are these reducing agents or the oxidizing agents?
Oxidizing.
Yeah, so this is showing oxidizing agents here. And the other thing you'll notice is there's numbers here. So it goes from the strongest oxidizing agent. An oxidizing agent causes oxidation. It's causing something else to lose electrons. So the strongest oxidizing agent is the greediest of them all. It's the one that wants the electrons the most. And look who's at the top of every chart we're going to find is fluorine. So it all comes around. It's all related to, but there is a full hierarchy. It doesn't follow a perfect path. And this would be our weakest. And it makes sense. If you look at the weakest, the one that doesn't want electrons, these are the alkali metals. The alkali metals do not want to gain electrons. They don't want to be back here. They liked being a +1. And the earth metals. And all right. And so that's why we're seeing negative potentials. Where this chart came from, so these are the oxidizing agents. On the other side are the reducing agents. So on this chart, what is my strongest reducing agent? If my strongest oxidizing agent is the fluorine, what's going to be my strongest reducing agent?
The lithium.
It is. So it's just like when we did acid base. The stronger the acid, the weaker the conjugate base. So our weakest oxidizing agent forms the strongest reducing agent. So, so the lithium solid, because you're going to see these questions show up in your study set and worksheet and places. So you don't want to just say lithium because lithium is the ion where you can just show the charge, or lithium solid. So the reducing agents are the opposite. Now somebody said at the beginning, so the arrows, we show these reactions as one way. but we can flip the reaction. So the reactions are written always as reductions, and where they made the chart from, I don't know who it was, but somebody declared that the hydrogen half cell was the standard cell that everything else was compared to. So if you have 2 hydrogen ions and 2 electrons and form hydrogen gas, anything you compare to it and then measure, and they just said, let's just assign it as the 0. So they just made up the number. And then everything else came from that. And the unit they gave it was a volt. So capital V, this is for a volt. And the unit is actually a joule per coulomb. So the J is for joules. Something we're going to have to be careful of because we're going to be doing conversions to delta G's. And so realize we'll have to do an extra step to change it to kilojoules. And the C is for coulomb. And I am not thinking how to spell coulomb at the moment. Wow. There's a double letter. All right. I can't remember which letter is double. It always fascinates me because so many years I wrote on the board, and writing down on paper, my brain doesn't work the same. It sees everything different. But Coulomb, when you take physics, Coulomb's a big guy in physics. So he did a lot with Coulomb's law and charges and stuff. So a Coulomb is, we're talking about the charge unit of the electron. We're going to see this unit show up. Where this is going is if we go back to this one on the bottom of that page, our little battery that we drew is the copper one. You can find the copper, and you have to be careful because some of these show up on this chart in different places. So the copper actually is only showing up once. Oh, good. If you look, there's some of them because they have multiple charges. They show up in a couple places. And of course, I'm not finding them right now. Well, like iron here is iron +3 to an iron +2, and then lower it shows iron +2 to the iron solid. So just be careful when you're using the chart that you find the correct one. I thought there was a copper 1 on this chart, but that must have been not the one that I put on here. And so this is exactly how our reaction is written on that previous page. The copper ion +2 electrons, the copper solid. And it gives us a potential. It's E naught. Does anybody remember what that little naught stood for?
The standard.
It means we're at standard conditions, which means we're at 25 degrees Celsius. And we're also assuming everything's at 1 molarity. All right, so that's the number for that one. When we look at the zinc, they can help me find zinc. There we go. Zinc's down below on the chart. So here's our zinc. It's backwards. It's flipped. So the anode is always flipped. We're working with positives and negatives. So the one that is flipped, which is always the anode, the equation that flipped is you just change the sign. So zinc going from zinc positive to zinc solid was a negative. So now it would have an E potential of positive 0.763 volts. All right. So our overall is we add them. This is how I do it because it's consistent with what we did with delta G's, delta H's, delta S, that if we flip the equation, we change the sign and then we just add them together. If you go online, they're going to do it a different way. They'll get the same answer as me. My way's better. So our E net, and we put that little symbol there, again means standard. That means the chart. And we just add those two numbers and we get 1.00, did I do 337? we get 1.100? I think so. Yeah. All right. Positive means it's spontaneous. What does spontaneous mean?
LTG,
Product favored. Anybody else? He's correct.
The K is bigger than 1.
It's going to mean we are going to relate it to K. So you would, and I think that's where you were going, Damon. The delta G, when we calculate it, will be
negative.
negative. K will be greater than 1, and this E is positive. Those, when I ask you to explain today on your worksheet, you're just saying that these two go together. Spontaneous reaction, the E is going to be positive, meaning our delta G will be negative. K is greater than 1. And what all this means is it's product favored. It's a go that once you hook it up and the battery is spontaneous, it's going to work. If you get a negative E, what's that going to mean? Well, the opposite. It means it's not going to work. You're not going to get anything out of it. You're going to have to plug it into the wall. It means it's non-spontaneous, which means you have to plug it in to make it work. That's going to be electrolysis, which we'll look at on Monday. So this pretty much summarized all the words on the next page. So we're going to go to the next page, and it's called a potential difference. Again, a volt is joules per coulomb. And there you go. I wrote what an electron, when you guys take physics, you get to learn this number. We've been always doing that charges of electrons are -1 and protons are +1. But your teacher, including me, would have said we're doing a relative charge, that they're equal but opposite. They do have an actual charge, which is measured in coulombs. This is not an exact number. There's people who spend their whole life doing it. And what a volt is called the potential difference. It is the driving force for the electrons moving between the electrodes. It is also called the EMF, or the electromotive force, or the cell potential. So usually I ask you, what's the cell potential? And this is the correct way to write it. I wrote E net, but it's actually E cell. So those were called the half cells that we were drawing on the previous page. And I forgot on Thursday, my neighbor gets her yard done. So I'm competing with the guys out there. I'm fascinated. Everybody waters their lawn. It's like, just let it go dormant. It's happy. And somebody had answered correctly. And this was a question during my office hours. So that E naught, we saw that with delta G naught meant standard. And that meant that everything's at 1, that you have 1 molar, you have 1 ATM, you have 25 degrees Celsius. Now, this is the part that's bizarre, is you start intermixing. If it's a gas, you're in ATMs. If it's aqueous, you use molarity. That's just how it is. It was a question that came up with the worksheet, that whatever K is given to you, you just go with it. It doesn't matter if it's a KA, a KB, they just go with it. I don't know why. All right. And there's lots of words here. I highlighted the two. Oh, right. We just talked about this. That's always shown as reduction. And that if we reverse it, we change the sign, and that we're looking for a positive. The other thing, and it's going to come up when we do the math, we talked about 1 and 3, that the top is the better ones, but it is an intensive property. The number of electrons are going to be important, but we're not going to be, you'll see as we go through the math. It's an intensive property, so it is the concentration, not the quantity, which is kind of weird to think about. But so I'm going to pause us. You guys are going to do 2 things with each of these, 3 things actually. You can write the half reactions. Oh, I know what I was trying to say. So like on this one that we doubled the aluminum, that doesn't matter. You don't ever double the E. That's what I was trying to say here. So do not double the E or cut it in half or whatever. So like here, my aluminum is doubled. That's to get the number of electrons. So the number of electrons does matter. So like for the tin, you're not going to multiply the number here by 3. You just go with it. So I recommend writing your 2 half reactions. You know which one you flipped, writing your 2 E's and finding your E naught. And then you're going to try this. So we have to talk about N. N is just like N was in gas laws. What does N represent?
Moles.
It is moles, but is specifically moles of electrons. That is where these numbers matter. So if we look at our first equation, we have 2 aluminums going to 2 aluminum ions. There's 6 electrons. So when you look up your cell potential for the aluminum, you don't double it. But that 6 is important because it's going to be your N number here, is 6 electrons. Does anybody know what F stands for? It's named in honor of somebody whose name starts with an F. It's Michael Faraday, who was somebody else who didn't have like this highfalutin education. He actually was a very poor person, and was Humphrey Davy's assistant. And he's the guy who figured out how to make electricity. There was another guy in the US who did it, but the United States, this was in the late 1700s, United States wasn't very important a couple hundred years ago. Right, and then this E is your E of the cell that you're going to calculate. Once you find delta G, if you want, you can do delta G equals negative RT, natural log of K, and even find K. There is a formula that directly changes E to K, but like why bother with another formula when if you find delta G, you can change it to K. So I'm going to pause this. You can take a 5-minute break, or you can try, I would recommend trying at least one of these. So write your 2 half reactions, find your E, and then see if you can find your delta G and even your K. And I'm going to pause this. All right, if you're working on it, you think you're getting it, keep going. I'm going to walk through this first one. So split into your 2 half reactions, or what you're probably going to be asked to do is figure out your half reactions. So the tin, the 6 electrons, they're usually written first, but I fortunately blocked myself. All right, so the aluminum is the one that we have to flip. The aluminum's down near the bottom. So something that if you're ever asked, which you will be, oh, it shows up here. We'll deal with it there. So the one that gets flipped, which is the aluminum on the chart, it then becomes a positive 1.66 volts. And the tin is negative 0.14, and then just adding them. So again, I do it different from apparently everyone else. I again do it just how we did it with delta G. So I flip the equation and change the sign and then just put them back together. Yeah. All right. How we would take that then down to the bottom is for the delta G, we would have negative N, so negative times the 6 electrons, which is that number of electrons that has to cancel out. Faraday's constant, which is 96,500. Coulombs, shoot, I can't believe I just forgot it. Really? I have it written in the notes somewhere, and it's a page I lost. Sorry. Oh, I was right. Coulombs per electron. All right, so it's coulombs per electron and then times E, which is our 1.52 volts. A volt is a joule per coulomb. One more piece we want to add. So our electron will cancel, our coulomb will cancel, and then the joule, 1,000 joules to 1 kilojoule. So this is a constant, Faraday's constant. And that's just what the number is, like when we've used R and all different constants. We want to go to kilojoules because delta G's are huge. So I always add that last step. And so for our first one, we end up with negative 880 kilojoules. And then if you wanted to go to K, you would plug into the delta G divided by RT and write e to the power. A question that came up on the worksheet today by several people, on the worksheet number 11, I give you K and you're solving for delta G. So if you know K, you just plug in and solve for delta G. You can ponder it. Our answers make sense. We got a positive E, so we got a negative delta G. That's for example A. For example B, our 2 half reactions is the chloride going to the Cl2 gas. So the electrons are on the product side. So this, and then my other one is going to be the electrons on my reactant side plus the bromine liquid. And I know it's going to come out negative, it does. It doesn't make sense for the chlorine to be flipped by the bromine. So when we look on the chart, we would find that the chlorine's up here and it's the one that gets flipped. So the chlorine was positive 1.36. So this gets flipped to a negative 1.36. And my bromine is positive 1.08. And those are volts. Make sure you show your units. So when I add them up, I get a negative cell potential. If I give you the equation, you go with how my equation's written. You can get a positive or a negative. You just go with it. This means we have to plug this one in. To try to make the chlorine gas, you got to plug it in. It's not going to work with bromine. That makes sense from everything you learned. Go back to 151 or 221. Chlorine's greedier, it's higher up. It's going to be the one that wants to steal the electrons. It's not going to give electrons up to bromine. It would give them up to fluorine and oxygen because it doesn't have a choice. But if we found our delta G, it's a negative, and then there's only 2 electrons in this one. You can just write F for Faraday's constant and then negative 0.28. So this negative at the beginning is always going to change your units. And then you're going to always, it is the most missed thing on the next celebration is everybody forgets to change it. In this case, divide by 1,000. And our answer comes out positive 54.0 kilojoules. And that answer makes sense. So this is for B. We had a negative E. So we got a positive delta G. All that means, if you get that, is it's non-spontaneous. It's going reverse. It's reactant favored. To make it go forward, we'd have to plug it in. Questions? All right, on C.
What's the
Go
number
ahead.
of the joules when it's like to the delta G?
Sorry, you broke up. I couldn't understand. Say it again.
Oh, sorry. The number, the joules on the delta G equal to 2 negative.
What, this?
Yeah, the one next to it.
That's F.
The-
That's
Oh,
actually
F,
what the,
got it.
that's how the constant's actually written. Bill Gates doesn't know the constant. So it's actually written as a really fancy F. You can write it however you want, but you can write the number in, it's this number. I just, like when I write R, I just write R instead of always writing the number out. And so you can just write the F, or you can write the number in, because it's always that same number. So thank you again. I was waiting for that question. And then this is, so you would state your formula and then plug in. The first time I did it, I actually recommend you do it the way I did it the first time. So Major's question, every single one of you, I don't know who's here other than Damon, because all of your cameras are off, but the first time I did it, I showed all my units. Somebody was commenting this, Max was commenting this earlier, that, yeah, when you show the units, you can see how things cancel out. So a volt is a joule per coulomb. And then writing Faraday's constant, that was coulombs per electron. And you kind of lose all that if you just write like the F and stuff. And then you lose that, hey, this is in joules, not kilojoules. And then you don't understand why you get a bizarre answer. So yeah, thank you. I recommend doing it this first way. You guys get so much time. It's a little ridiculous. So on this last one, I did not give you the reaction. And the question would have a full wording with it. You're trying to make it work. So make it spontaneous. You're trying to make it have a positive E. So the way you use the chart to do that is we find the zinc, which was down here, and we find the nickel, which is up there. Whichever one is lower flips. So the lower one, so lower on the chart, my camera got moved since yesterday somehow. Lower on the chart flips. So whichever two I give you, the lower one flips. So we're gonna make it go on the chart. The nickel stays how it is. Nickel positive 2 plus the 2 electrons. And that was a negative 0.25 volts. But the zinc I'm going to flip to make it zinc solid, going to the zinc plus the 2 electrons. And that means I change the sign. So this becomes a positive 0.763 volts. And when I add them together, that's what I would get. That ends up being the biggest question on the next study set and the one after it. So always the lower one, if I give you the equation, you have to go with how I give you the equation. If I say make a voltaic cell, you have to flip the lower one on the chart. So like on your celebration, and actually I think on the worksheet, I give you a mini chart, but on your study set, and I posted the study set, but I didn't put any answers on it. So all of you are eager beavers. That's great. You don't have answers, and the rest of you might want to give me a day so I get a chance to breathe and put the answers on there, and then I'll post it. I ran out of room to solve for my delta G at the bottom of my page for C, but if E is positive, what should we get as our value for delta G? This is like the big picture question.
Negative number.
Negative delta G.
Negative, and Captain's back. All right, what kind of K value should I get if I use this wonderful formula then?
Greater than
Greater
1.
than 1.
Max, were you like talking and you didn't realize you're muted? Maybe.
Yeah, I missed the
Okay.
button.
That's funny. All the other times you were at the bottom of the screen, I guess, because you didn't figure out how to turn your. It's been like only a whole year and you still can't find the button. So K is greater than 1. delta G, E is positive. So that's the big take home picture where all of this comes together is with this. So we have a little bit more to do. I promised today would be a longer day. Is there any questions? Somebody just got kicked out. Paul, did you have a question? You suddenly
No.
popped up. Okay. If you want to like pop up, you have to raise your hand and then it like you supersede me apparently. We're gonna do one more, maybe two. This is highlighted because we're gonna use this. This is called the Nernst Equation I can't remember his first name, but a gentleman named Nernst who figured this out. This is the full formula, which I didn't highlight because R is a constant, F is a constant, and T, if we're always at 298, we're assuming that this is always at 298 Kelvin. And in here, we pretty much stick with that. So as long as we stick with that, if you take R times T divided by Faraday's constant, you're always going to get this number 0.0257. So everyone pretty much simplifies it. And then we put it over N, and N again is what?
Number of moles of electrons.
The moles of electrons in your equation. So like this one, you can see it's going to be 2 electrons. So in the 2 half reactions, it's the number of electrons that cancel out. So you can just say electrons, or it's technically electron moles. And then this is a question that came up in my office hours, was about Q. Well, Q, we talk about Q. When I first introduced it, it was just, hey, we're mixing stuff. You're trying to figure it out. What it really means is you're not at standard conditions. And so it is the products over the reactants. And if you have K, this E on this side of the equation is going to be a 0 and it's gone. And so you end up with E naught equals 0.0257 over N natural log of K. So it's a way you can change E to K. This E becomes a 0. And then you just set this equal, you lose that negative. But I just do it with the delta G because it's just as simple. All right, we can see we have non-standard because we have the iron here. So before we do this, we're going to actually answer the question at the bottom, why it's going to make sense. So the thing that is not standard is the iron. So this is something that happens at the end of actually today's worksheet and Monday's worksheet and Wednesday's worksheet is I'm going to change something and then you're going to have to explain it. The problem that happens for 50% of you, and probably all of you 50% of the time, is you look at the answer you get and use the answer to explain. You're trying to explain why that answer makes sense. So the answer is at the end of it. So the change is that we lowered the iron +2. That has to be the starting point. And so Paul, this was like the question during office hours. It's like on the first set of questions on your worksheet. So the iron is the piece that is the biggest change. So standard again is 1. And in this case, the iron ion, the iron +2, solids we ignore, right? They're not going to be part of our K or Q expression. So we can ignore the solids. It's just the ions that we're going to care about. If we decrease the iron and it's a product, what does our favorite Le Chatelier's principle say is going to happen?
It's going to shift reverse.
It's going to shift. Go ahead, Paul.
In reverse.
No. Iron's on the side of the arrow. You heard him mumble it and then you repeated it. It's going to shift towards the iron because you decrease the iron. So it's going to shift forward. If it shifts forward, what do you think is going to happen to the value of the E? It's either going to increase or decrease.
Increase.
It goes up because the E value is favorable, positive is favorable. So as you keep going higher and higher, if it was delta G would decrease. If it was K would increase. But we're going to be looking at E. Delta G would decrease, K would increase. You can ponder all that. It's a whole big connection. Let's do this. To do this problem, this was the other question. So on the worksheet, you do it with delta G's, and you have to use the other set of notes. But that E is using the chart. So you first have to calculate this E. We're going to have 2 electrons, and you're going to do products over reactants. And pause this. I'll give you a moment if you want. If you're really good, you can try. We're going to try this one too. So I'll pause this for a moment. Do this again. However I write the equation, you have to go with it. Unless I say, hey, first, let's write the favorable equation. So on all of these on this page, we're just going to do 1 and 2 today, and then we'll do 3 and 4 in electrolysis and the basic solutions on Monday. But I think it's helpful to write the half reactions. Sometimes we'd be asked, like, what is the anode? What metal is the anode? So if you're asked that, you want to look at your half reactions. The iron is losing. It's my Leo, so this is my anode. Or I might say, hey, what's the polarity of the cadmium? So you'd be like, oh, cadmium's GR, so it's the cathode. And the cathode, we're going to assume this is positive. I have to know that for sure. Actually, for the positive negative, I have to do my calculation. So I need my chart. And on the chart, the iron is the one that gets flipped. So it becomes a positive 0.44. And the cadmium is written and it's a negative 0.40 volts. So I know it comes out positive because, yeah, on the chart, the iron, and be careful because the iron's 2 places on this chart. You want the one with the +2 to iron solid. The cadmium, the lower one was the one that was flipped. So it's going to end up working. We come out with a really small cell potential, 0.04 volts. Cell potentials are always really small. You don't have to show the plus and minus. You're going to see me always showing it because that's like the key to all this. And then we're plugging into this. So E is going to equal 0.04 volts minus the 0.0257. It's just a number. We don't put a unit on it. Over our 2 electrons. And then natural log, this is going to be the iron on top, the 0.01, over the cadmium, which was 1. So we ignore solids and we put it in our calculator and our prediction was right. When we do this math, you would state your formula, get in the habit, which you've been in. Don't lose it now. We're 1 week from being done. 1 week from now, you can go do everything you want to do. You can do that now by meditating. All right, so 0.0992 volts, or you can go with 2 sig figs, 0.099. And so our prediction was right. This is the effect, the increase in E. So it's not that E increased, which caused the iron to be down. It's that this is the cause, the decrease in iron, shift it forward, and our E went larger. All right. So yeah, try our next one. At least write your 2 half potentials. You can, I'm going to pause this. You take a break. All right, I'm back. So write your half reactions. If I give you an equation, it can come out positive or negative, and this one's going to come out as negative. And I did that on purpose. All right, and then put our electrons in there. So the silver is gaining, the mercury is losing. And so this is non-spontaneous. When we look them up on the chart, the silver is positive 0.8 volts, and the mercury is the one that we flipped. It was higher up. So you can immediately know when you look at the chart, that's not going to work. And so we get a non-spontaneous. But we can still do all the calculations. So this is one of the tricks with Le Chatelier's principle, because we're going to actually be able to change some of the concentrations. So you want to state the formula, and rather than stating it exactly like this, this is how I would recommend saying it. The E equals E naught minus 0.0257 over N. And then instead of saying natural log of Q, actually write in what Q would be. So we'll have the mercury on top, mercury ion, and the silver ion, the reactant, on the bottom, but the silver is squared. So this was a question on the first lab. Anything we do to the silver, any small change is going to change it significantly because it gets squared. However, we make a much bigger change to the mercury. So often there's multiple changes, but you want to look for the biggest change. So by decreasing the mercury in our explanation, we decrease the mercury ion, so it shifts forward. Again, we ignore solids and liquids because it is equilibrium, and that increases the value of E. So we would just plug in all our numbers. So this net number, the negative 0.055 volts minus, we have 2 electrons, and then natural log. All right, and we should get that number. Your volts should be hitting the same as mine. And then your explanation would just be, we decreased the mercury significantly. It shifts towards that mercury ion because it's a product. So when you decrease something, you shift in that direction. And so if you shift forward, E is going to get larger. All right, you could do calculating delta G first and then K. I'm going to do K. So like I said, you can, if you're somebody who wants another equation, it would be E naught equals 0.0257 over N times the natural log of K. You can also use the one you're using today, delta G, when we actually had to learn, memorize stuff. I always eliminated that because it was just one more piece of thing to have. Students actually did brilliantly, and they were able to, this next exam, they all finished in an hour and a half because it was just there. In your brain, it's a lot faster than finding it in your notes. And so they would practice and they would just have it down. The other comment, if you did use it this way, you're going with E naught, which was the chart value. So the equilibrium constant, the delta G, you're always going back to whatever your chart value was. And this one, we're solving for K. So we would do E to the power of the E naught divided by the 0.0257, but then times the N. So anyway, you would do that. Or you can find delta G first. So our delta G is negative, and Faraday's constant. Again, it's always written as a funky F. You don't have to write it as a fancy F. And then E naught. So that's technically both ways. So when you find your K, you should get a 0.015. You could then plug the K into this and solve for delta G, or you can go from the E. They all come together. I think it's easier to do this one and then that one. And that's our answer. And then you will typically be asked to explain. So one last time is if we have a negative E, we would expect a K less than 1 and a positive delta G, because all of those mean non-spontaneous or it's reactant favored. So again, if I make something non-standard, we're using Le Chatelier's principle, but if it's all the standard stuff, we're just saying how these all fit together, if that makes sense, hopefully. Any questions? So thank you yet again for joining me. We got some, yeah, we'll stop. And then did